Welcome right back to our System Design Explainer. Today, we're jumping straight into day 6, and it's all about the critical mechanics of load balancing. If you've ever found yourself wondering how the absolute biggest platforms on the internet stay online without breaking a sweat, well, you are in the exact right place. Let's get started.
So think about this for a second. What actually happens when 1 million users hit your server at the exact same time? Well, if you're rocking just a single server and a massive wave of traffic comes rushing in out of nowhere, it's going to max out its CPU, run entirely out of memory, and completely crash. For absolutely any business, downtime is a total nightmare. We're talking lost revenue, incredibly frustrated users, and a seriously damaged reputation. This single point of failure is exactly what we have to solve.
Here is our roadmap for today's explainer. We'll start with why we use load balancers, then compare layer 4 and layer 7, look at traffic distribution algorithms, dive into health checks and failover, and finally design for high availability.
All right, section 1. Why use load balancers? The problem with a single server.
Basically, a load balancer is a system that acts just like a traffic cop. Picture a massively busy downtown intersection. If every single car tries to merge into one lane, you get instant gridlock, right? The whole system just freezes up. But if you put a highly efficient traffic cop right in the middle of it all, they start pointing cars to different lanes to keep things moving. A load balancer stands right in front of your servers and distributes those incoming requests, ensuring no single server ever becomes overwhelmed.
Let's move on to section 2, layer 4 versus layer 7, the routing rules.
So you essentially have two main flavors when it comes to routing. Layer 4 operates at the transport layer. Think of this as being all about pure raw speed. It only looks at surface-level information, mostly just IP addresses and port numbers. It doesn't open the envelope to see what's inside the message. It just reads the address on the outside and forwards it instantly. It's incredibly fast. Layer 7, on the other hand, operates at the application layer and it's all about smart routing. It actually opens that envelope. It looks at the HTTP data, the headers, and the specific URL you're trying to reach. Because it knows exactly what the user is asking for, it makes super intelligent routing decisions, like routing all video requests to a dedicated video server. So as a system designer, you have to choose the blazing raw speed of layer 4 or the data-aware precision of layer 7. Which brings us right into section 3, traffic distribution algorithms, specifically round robin and least connections. Okay, so how does this traffic cop actually decide where to send you? Well, round robin distributes requests sequentially. Imagine dealing a deck of cards to 4 players. You give one card to player 1, the next to player 2, and so on, looping right back around. It's a perfect algorithm for evenly distributed, highly predictable traffic where every request basically takes the same amount of time to process. But what if your traffic is super uneven? That's where least connections comes in. It routes new traffic to the server with the fewest active users. It's just like walking into a grocery store. You don't just blindly walk up to register 1, right? You look for the shortest line. This algorithm actively monitors server load and sends the request to the one doing the least amount of work. It is an absolute game changer for uneven traffic or applications where users have long, complicated sessions.
Now for section 4, health checks and failover, the safety nets of our system. Let's walk through the exact steps of a failover, because let's face it, things break. Step 1, a server goes down unexpectedly due to hardware failure or a crash. Step 2, the continuous health check fails. See, our load balancer is constantly pinging our servers behind the scenes asking, hey, are you healthy? The literal second a server stops responding, that health check fails. And that instantly triggers step 3, the load balancer yanks the dead server out of the rotation entirely and reroutes all new traffic to the remaining healthy servers. Disaster is completely averted, and your users have absolutely no idea anything even went wrong.
Let's tie it all together in section 5, designing high availability, the practice. So, when you're gearing up to build your next highly available application, this is your ultimate playbook. First up, deploy multiple servers so you can handle both your baseline and your crazy peak loads. Second, implement a load balancer to act as your primary traffic controller. Third, select layer 4 for that raw speed or layer 7 for smart application-level routing. Fourth, choose the optimal algorithm for your use case, whether that's round robin or least connections. And finally, enable strict health checks and automated failover. If you do all that, you've just designed a highly available system that can survive massive traffic spikes and hardware failures alike. You've built an incredibly resilient system today. But here's a thought to leave you with. Your balancer is set up perfectly, traffic is flowing completely smoothly, but what happens if the load balancer itself goes down? Seriously, what balances the load balancers?
Think about that massive single point of failure. Until next time. Thanks for joining me on this explainer, and keep building.